In this video, we solve problem 11.1.080 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. It has two parts, and the problem statement says, determine the tension in each cable supporting the given load for each figure. Assume that M1 equals 4,000 pounds and M2 equals 5,000 pounds. Round your answers to one decimal place. So we want the tension in each cable. And we've got a cable here and a cable here, and those are the two cables that are supporting this weight. And we're told that M1, which you might think represents a mass, is actually, it's a weight, it's 4,000 pounds. Kind of bothers me that they're using M for that weight instead of using it for the mass, but that is okay. And we could just as easily draw that vector starting at the point C. What we're interested in are the two tensions, one through this cable and then the other through this cable. Now, the fact that we need from physics is that the sum of the forces acting on any object is equal to the resultant force. And this whole system, we assume, is not moving. So that means this force has to be completely balanced by these two forces. Tensions are just forces in cables here. This tension plus this tension plus this tension has to be the zero vector. I will call this tension T1. I will call this tension T2. And I think I'll just redraw my picture over here. Got T2 and T1. And some weight pulling straight down. We're using this fact from physics. The sum of the forces is equal to the resultant force. And since nothing is moving, that resultant force is the zero vector. And this is easy enough to set up. We can set up an equation. All we have to do is find the x and y components of each of these tensions and then add up all the tensions, or add up all the forces in the x direction and add up all the forces in the y direction, and use those to come up with a system of equations for the magnitudes of T1 and T2. And then we'll solve for T1 and T2, and then we'll be pretty much done. Okay, so we need some angles here. Now you've got options. I could draw a right triangle, or actually I could draw a vertical line right through that C here. And then you see a right triangle over here and a right triangle over here. With that in mind, since this angle is 90 degrees, if this is 30, this has to be 60. And if this is 50, well, this angle plus this angle has to be 90. So that would be 40. Or if you prefer, if this is 60, then this angle from the horizontal is 30. And if this is 40, then this angle from the horizontal is 50. Okay, so our tension T1 can be split into two parts, one that pulls in the x direction and another that pulls in the y direction. Now, I don't know the magnitude of that tension, so I'll just list it that way as the magnitude of T1. But the adjacent side of that triangle will be given by the magnitude of that triangle times the cosine of this angle. Because remember, cosine of an angle is adjacent over hypotenuse. So the adjacent side would be the hypotenuse, which is this, times the cosine of the angle. So we'll have cosine of 30 there. And then for the y component, that's opposite the 30 in the triangle. So we'll have the hypotenuse times sine of 30, because sine of an angle is opposite over hypotenuse. So we've got that. Now I need to find the components of the vector T2. So T2 looks like this. And I'm going to choose to use that 50-degree reference angle. So I need an X component here. Now, because it's pulling in the negative X direction, and I've already chosen for this to be the positive X direction, I'll have a negative magnitude of the vector T2. And again, because it's adjacent to that 50-degree angle, we'll have cosine of 50. And again, the negative comes from the fact that it's going in the opposite direction from this guy, and I've already chosen to make that the positive X direction by making this guy positive. Okay, so we've got cosine, or the magnitude of T2 times cosine of 50 times the -1 because of the direction. And then we've got over here for the Y component, it's going to be the magnitude of T2. And since that'll be opposite the 50, it's the sine of 50. And then for our weight, we know we've got a weight that's pulling straight down. So there is no component in the X direction. It's not pulling left or right at all. But we've got 4,000 pounds going straight down. So I would call that negative 4,000. We add these three vectors together and we're supposed to get the zero vector. So this plus this plus this equals the zero vector because nothing's moving. That means this plus this plus this must equal 0, and this plus this plus this must equal 0. So you add the X components together, you add the Y components together, and then because we're getting the zero vector, the sum of the forces in the X direction should be 0, and the sum of the forces in the Y direction should be 0. So we'll write that this way. Sum of the forces in the X direction, that's this plus this. And I'm adding something negative, so I can just subtract it. That equals 0. And the sum of the forces in the Y direction is this plus this guy minus 4,000 equals 0. Okay, so that's where we're at. Now from here, we've got a system of two equations and two unknowns. It looks more complicated than it is because of the trig functions, but these are just coefficients and these are just unknowns. So what I would suggest is solving this first equation for either the magnitude of T1 or the magnitude of T2, and then substituting into the second equation. Now you can do this in whichever way you want. I think I will solve for the magnitude of T1 in terms of the magnitude of T2. So to do that, I will add this to both sides. And then I'll divide both sides by that 30 or cosine of 30 degrees. And then I will make a substitution. Instead of writing this magnitude of T1 right here, I will fill that in right there. So I'm substituting this guy for this guy. We have this magnitude of T2 times cosine of 50 divided by cosine of 30 times sine of 30 plus the magnitude of T2 times sine of 50. And we want to get the magnitude of T2 by itself. So I'll add that 4,000 to the other side, or add that 4,000 to both sides, which gets rid of that and then gives us that number over there. And then of course, this can be simplified a little bit. Sine of 30 divided by cosine of 30, which is exactly what we have there. We can rearrange that. That would be tangent of 30. So I've got the magnitude of T2 times cosine of 50 times tangent of 30 plus sine of 50. I'm just factoring that magnitude of T2 out from both of these guys. That equals 4,000. And so the magnitude of T2 is 4,000 divided by all of this. because there's a lot going on here, I would recommend that you handle the expression in the denominator first in your scientific calculator, and then take 4,000 and divide by that answer. That's what I'll do. So I first confirm that I'm in degree mode, and I am. Then we'll do cosine of 50 times tangent of 30 plus sine of 50. We get that answer. And then we want 4,000 divided by, and I'll just use the answer button, equals. And I get the magnitude of T2 is approximately 3,517.5. And our tensions were, or our weight was given in pounds, so our tension will also be in pounds. So that gives us T2. And remember, T1, or the magnitude of T1 was the magnitude of T2 times the cosine of 50 divided by the cosine of 30. So I will just use my calculator for that piece now. So multiply by the cosine of 50, multiply my last answer by that. And then we'll divide by the cosine of 30. And we get approximately 2,610.8 pounds. So that is the magnitude of T1. Now, the way WebAssign lists it is a little unusual. They don't call this T1 and T2. I believe they just list this as a vector from C to B. So they'll say CB equals, you know, some number of pounds, and CA equals some number of pounds. I really hate that notation because it looks like that they're implying a vector actually equals a scalar, and that vector that starts at one location and goes to another location is not the same as the tension in those cables. So I really hate that WebAssign does this, but this is how we will have to answer, or how we will have to enter our answers on WebAssign. So the one that we're using for T1 is the vector from C to B. And they actually might have this listed in the reverse order. They probably put the A first, but this is what I was calling T1. The magnitude of T1 is this 2,610.8 pounds. And the magnitude of T2, should put some bars around that to indicate that it's a magnitude. Even though they didn't, it really bothers me. The magnitude of T2 is 3,517.5. Actually, on second thought, as I'm looking at WebAssign's answers, they have these flipped, but I'm certain that our math is correct here. So I don't know why they have these flipped. Perhaps they meant to list the vector CA first and then CB, but for some reason they list CB, then CA, and then they've got these two numbers flipped. But they're incorrect. I'm pretty sure that this solution method is accurate. Let's check. Can always check our work with a problem like this. Remember, we've got this picture. We've got A over here, C over here, B over here. This is not to scale. And this is what I was calling T1. And this is the tension that I was calling T2. T1 had a reference angle of 30 degrees over here, and T2 had a reference angle of 50 degrees from the horizontal. And we had some weight pulling down at the same time of 4,000 pounds. Now, if we've done everything correctly, the tension pulling to the left and the tension pulling to the right should match each other. It should be exactly the same. Now, we use decimal approximations, so we might have a tiny rounding error. But if we actually compute the component form of T1 and T2. Those x components should be the same, but with opposite signs so that they cancel each other. So remember, T1 was this vector with this component form. We had the magnitude of T1 times cosine of 30. And then we had the magnitude of T1 times sine of 30 as our x and y components there. The magnitude of T1 was that 2610.8 approximately. I've actually got the exact answer right in my calculator right now. So I think I'll multiply that by cosine of 30. This is approximately 2,261.0 pounds in the x direction. I'll divide out that cosine of 30 that I just multiplied by. So now I'm back to T1. I want to take that and I want to multiply by sine of 30. And my y component is 1,305.4 approximately, that many pounds. Okay, so that's our T1. And then let's look at T2. We know it should look like this. We've got T2 cosine of 50, T2 sine of 50. We're talking about magnitudes here. That sine or that y component is going up, so that should be positive. The x component is going to the left, so that should be negative because we're treating this as the positive x direction. And the magnitude of T2 was that 3517.5. So we'll take approximately negative 3,517.5, and we'll multiply that by cosine of 50. We get negative 2,261.0 pounds. Now we'll take our approximate answer there, 3,517.5, and multiply by sine of 50. And we get 2,694.56, which is approximately 6. Okay, and remember that weight that we're balancing did not pull to the left or right at all. So we've got 0 as our x component and negative 4,000 as our y component. Now, if I add these x components together, so this x component plus this x component plus this x component, I should get 0. And we see that we do. This is 2,261 pounds. This is negative 2,261 pounds. So we're pulling with exactly the same magnitude of force to the left and to the right. So that all balances out and we get the 0, or we get a 0 for our x component there. Now, this weight is pulling down with 4,000 pounds of force. In order for these two tensions, excuse me, my calculator just fell, to support that weight, this tension plus this tension, or in other words, the magnitude of that force that's going straight up and the magnitude of that force that's going straight up, the sum of those together has to balance that 4,000 pounds. So we know we've done this correctly if this plus this equals approximately 4,000 because we were rounding. So let's see. Got 1305.4 plus this 2694.6. And it's 4,000 pounds exactly. So we've just confirmed by adding the x components and the y components that the sum of those three forces is equal to the 0 vector. And that's the same as looking at the sum of the forces in the x direction and seeing that they're 0, and the sum of the forces in the y direction and seeing that they're 0. So these answers that we came up with are correct, but for some reason WebAssign flips them, it inverts them. They probably just meant to put this one first and then that one second. It's probably the issue there. Now, part B is set up a little differently. It's no big deal. We can still handle it. They didn't give us the angles this time, but they gave us some dimensions. They told us that this is 10 inches and that distance right there is 24 inches. So if this distance is 24 inches, that means this distance is 24 inches. And that means I've got both legs of this right triangle that's right here. And I also have both legs of this right triangle over here. So with those two legs, we can find either this angle or this angle. And then once we find either this angle or this angle, we can find the corresponding angle from the horizontal. Now you could always use the angles that are listed here, this one or this one or this one with your trig functions. Any one of them would work. But I think most of us are more comfortable with or have tended to work with angles from the horizontal more often. So I'm going to do my calculations using the angles from the horizontal. But obviously you could use this angle and sine and cosine in a certain way, or you could use this angle and sine and cosine in a certain way, as long as you are remembering that sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. And just like last time, WebAssign told us the mass was 5,000 pounds, which, I mean, they didn't say it exactly like that, but it really bothers me that we're writing M equals that. That's okay. They just mean that the weight pulling down is 5,000 pounds. So I'm going to label that with a W because that makes more sense to me as a weight. So we've got 5,000 pounds there. And I want the tension in this cable and the tension in this cable, just like before. But now we've got an extra step. We just got to do a little trig first. A little bit more trig. So if this is 24 inches, and I'm interested in finding this angle right here, the angle at A. I can use the tangent because I've got the side opposite A and I've got the side adjacent to A that is not the hypotenuse. Remember, the hypotenuse is opposite the 90. So I can use trig. The tangent of that angle A is opposite over adjacent. The opposite side has a length of 24 inches. The adjacent side has a length of 10 inches. So that means our angle A is the inverse tangent, or arctangent, if you prefer, of 24 divided by 10, or 2.4. I prefer to use the arctangent when I do math on paper, but the calculators use that tan inverse notation. You just have to remember that it's not 1 over tangent. That would be cotangent, and it's a totally different thing. Okay, so I've got this inverse tangent button right here. So I'll press shift and then tangent to get into my inverse tangent, and then type in 2.4, close parentheses, and I'm already in decimal mode. Sorry, degree mode, not decimal mode, degree mode. My answer for angle A is 67.38 degrees. Now that is an approximation, and this angle would be 90 minus that angle. And that means this angle is the same as angle A over there. So I'm not actually going to label it A because we're using the label C here. I'll just label it as approximately 67.4 degrees. Or you can use 67.38 if you want slightly more accuracy. Similarly, if I want the angle at B, so I'll just call that angle B. I'll use the tangent as well. Tangent is opposite over adjacent from right triangle trig. The side opposite B is 24. The side adjacent to B is 20. So that means that B is the arctangent or inverse tangent of 24 divided by 20, which is going to be 1.2. And I'll use my inverse tangent button again, shift, then hit tangent, and then plug in 1.2, close parentheses, and you get approximately 50.19 as that angle there. Okay, so now we have the angles from the horizontal, and once we have the angles from the horizontal, we can use those to come up with component form for this tension and this tension, and then we will add up the 3 vectors, set them equal to the 0 vector because we know our resultant force is 0. This mass is not sort of flying through the air. It's not going up and it's not going down. It's just steady. It's being held there by these cables. So everything is static. So we set the resultant force equal to 0. And then we'll just add up the forces in the X and Y directions. Okay, so I'll call this T1 again, one on the right, and then I'll call the second one over here on the left T2. So T1 has this component form. The x component goes right there. That x component is adjacent to our angle 50.19. The adjacent side is the hypotenuse, which is the magnitude of T1 times the cosine of that angle. Of course, all of this is approximate because we're using decimal approximations here. And the same, or something very similar is true for, the y component. The y component is opposite the angle. The opposite side is the hypotenuse times sine of that angle. And we handled T2 in pretty much the same way. I'm going to multiply each of those guys by the magnitude because we'll have the hypotenuse for each of these. We need an x component and a y component. The x component is that magnitude times the cosine of this angle because the x component is adjacent to the angle. But since we've chosen this to be the positive x direction and this is going the other way, that'll be negative. Or if you prefer, you could use the angle 180 minus that 67.4. I prefer to just look at the geometry. I'll use the right or the acute angle between 0 and 90 and the fact that it's going to the left to give me that negative sign. I think it's easier to think of it that way, as this is being positive and that is being negative once we've made our choice of orientation. Okay, so that is our x component. Our y component is the part of that tension that is pulling straight up, and that is opposite the 67.4. So we'll have the opposite side as the hypotenuse times the sine of that angle. And the weight is 5,000 pounds going straight down. So we've got an x component of 0 and a negative 5,000 pounds as our y component. And again, because nothing's moving, the weight's not flying through the air, it's not going to the left or to the right, it's not going up, it's not going down, everything is static. Sum of the forces is the resultant force, which is the 0 force or 0 vector here. So this plus this plus this equals the 0 vector, which means the sum of the forces in the x direction has to be 0 and the sum of the forces in the y direction has to be 0. So let's write that down now. Sum of the forces in the x direction is 0. So here is the magnitude of the tension in the x direction for that first tension. And then we're adding the magnitude of the tension in the x direction for the second guy, but since they're going in opposite directions, we have a negative there. I guess we could use that 3/8 to be slightly more accurate. That equals 0. And the sum of the forces in the y direction looks very similar, but we have sines instead of cosines. And both of those tensions are pulling up, so they're both positive here. So both of these are going up, that one's going down, so we've got the minus 5,000. And now we've got two equations and two unknowns that we can solve for the magnitude of T1 and the magnitude of T2. Okay, I am going to choose to solve for the magnitude of T1 in terms of the magnitude of T2 from this first equation. We do that by adding this guy to both sides. And then dividing both sides by this cosine of 50.19. Okay, and then we're going to substitute that down here. So I'm replacing this with this. So I've got the magnitude of T2 times cosine of the 67.38 degrees. And then I'm multiplying that by sine of this 50.2 and dividing by cosine of 50.2. And then I'll just rewrite this. And I'm eventually going to solve for T2 because you've got one equation with one unknown now, which is the goal when you're solving two equations and two unknowns. The next thing you want to do is get it down to one equation and one unknown. And then we just factor out that T2 because that's what we're solving for. Got the cosine of 67.38 there. Sine over cosine of this angle is the tangent of that angle. And I'm factoring out the T2 from this term and this term. So when I factor that out, I'm left with a sine of 67.4 over here. Or we're going to use the 67.38. 67.38 degrees equals 5,000. Okay, now I want to get the magnitude of T2 by itself. So I just divide. Easy breezy. And that is the magnitude of T2. Now again, just like last time, I would recommend that you handle the denominator first, figure out what the answer is, and then take 5,000 and divide by the answer. So we'll say cosine of 67.38 times tangent of 50.19 plus sine of 67.38, close parentheses, is equal to that. Now I want to take 5,000 and I want to divide it by my last answer. So I get approximately 3,611.3 pounds. Okay, and we know the magnitude of T1 is the magnitude of T2 times cosine of that 67.38 divided by the cosine of 50.19. So we'll multiply and then we'll divide. So I'm multiplying by that cosine. I already had my T2 in my calculator, so I'm just multiplying the answer by that cosine, and then we'll divide by the cosine of 50.19. Oops, delete. Close parentheses, hit equal, and we get 2,169.4 approximately. And that's pounds as well. Now in WebAssign, again, they are not asking you for the magnitude of T1 and T2. They just sort of do this vector CA and CB and ask you what those are equal to, but then they set this vector equal to a magnitude in pounds, which really bothers me. This is what they write. You've got a little box there where you enter the magnitude of CB. Then you have a box where you enter the magnitude of CA. But CA was just what we were calling T2, and CB is what we were calling T1. So what they really want here is the magnitude of T1 and the magnitude of T2, even though they've used inappropriate notation. Now the magnitude of T1 was that 2,169.4 pounds. And the magnitude of T2 is 3,611.3 pounds. Oops. Now, if we've done everything correctly, when we substitute those two magnitudes in here, then the sum of the forces in the x direction should be 0, and the sum of the forces in the y direction should be 0. Just to confirm, I will use the magnitude of T1, which was that 2169.4 approximately, and I'll multiply it by cosine of 50.19. So I get 1,388.9 approximately. Now, this one should be exactly the same, but with the opposite sign. So let's look at T2. T2 is, its magnitude is 3,106 or 3,611.3. And we multiply that by cosine of 67.4. And of course, we're multiplying by -1 because it's in the opposite direction from this guy. And we get approximately the same thing. So I have 1387.8 there. And on the other one, what was it? Oops, I think I chose the wrong magnitude. It's 2169.4 times cosine of 50.19. Yeah, another, I get 1388 and 1387. So they were close, not exactly right, but that's because the angles were approximations to begin with. And then we were using those approximate magnitudes for the tensions. Now I'm not going to do this time, but if you want, you can substitute in the magnitude of T1 and T2 here. If you add these two together, you should balance that 5,000 pounds of force that's pulling straight down. Let me know if you guys have any questions about that.